This is section 5.5, and we're still talking about area, and we're still trying to kind of figure out what that means in terms of calculus. So the essential question for 5.5 is still the same question that we had in 5.1, and that is how can we approximate area when the region is not geometric. So we're still approximating, and we're still looking at regions that we need, we don't have geometric shapes for. So just to remind you, that's the geometric shape we've been looking at in section 5.1. And this isn't in your notes, so this is just kind of a discussion. So let's take a look at what we talked about in 5.1. So here's that function that was the 1 plus 1/8 t squared. And here's our LRAM, so here's our points that make the left sides of the rectangles. We got 5.75 for the LRAM, and here's our RRAM, so now we let the right dots make the tops of the rectangles, and that was 7.75. So that's from section 5.1. And if we take a look at what that creates then underneath the function, our LRAM creates a situation where we have gaps underneath our function, which means the LRAM is an underestimate, or it's too small. And our RRAM creates a situation where we have extra flaps that extend above the function, and that means we have an overestimate and the RRAM is too big. So what we need to do is we're still working with approximation techniques. We just need to refine our techniques so that our approximations are closer to the actual value. So we talked about an MRAM, but the MRAM is problematic because the MRAM needs that point right in the middle between the other 2 points, and sometimes we don't have that. Like for this example in section 5.1, we had to go back and recalculate all those points, and that got to be time consuming. It is accurate though. We don't know, I mean, we can see that we've got some flaps and some gaps, and we can put the flaps into the gaps. We don't know if it's an underestimate or an overestimate, but we do minimize that, and so this is more accurate, but it's also a lot more work. So the idea is, can we get away with doing not that much work and still get this accuracy? And the answer is yeah, we can. So what we're going to do is we're going to kind of throw the MRAM out of the picture for a little bit. And instead of an MRAM, what if we just connected the dots on the function? So I'm just going to go from a straight line from here to here and here to here, and so on. Then if we look at the shape, and I'm just going to focus on this one region from 1 to 2. All the other regions behave similarly. But if we look at just this one region, then we see with a straight point-to-point line at the top, we end up getting this geometric shape, which we know is a trapezoid. And so the question is how can we use what we already have to find the area of this trapezoid? And we can do that by, and this is the graph on your sheet now, so go ahead and connect the dots on your sheet in your notes to create those trapezoids. And we're going to focus on this trapezoid here. And we're going to compare it to the LRAM and the RRAM. So our LRAM, between 1 and 2, our LRAM is 1 1/8 inch tall. And so we get this LRAM approximation between 1 and 2, which is too small. And our RRAM between 1 and 2 looks like that. That's 1 1/2 tall. And we know that that's too big. It's got a flap up there. So this TrapRAM is really close. In fact, that trap is those flat segments between the points almost follow the contour of that parabola perfectly. So let's compare the sizes of these. Here's our RRAM, and I'm going to overlay it with our LRAM, excuse me. I'm going to overlay it with our RRAM, and we can see that we have this extra height here. And take a look when I put the TrapRAM on top of that. So we can see that that TrapRAM just takes up literally half of that extra tab on the top. And so our TrapRAM value then is exactly halfway in between the red and the blue. And so if we know the red and blue values, then halfway in between would just be the average. So we can find that TrapRAM then by either averaging the LRAM or the RRAM together, or we can just go ahead and use the geometry formula and calculate the areas of the different rectangles. Different trapezoids. So for reasons I'm not going to get into, the actual area underneath that non-geometric shape is 6.6 repeating. If we go to the averaging of the two methods, our LRAM was 5.75, if you recall. Our RRAM was 7.75, and if we average those, we get 6.75 for our TRAP-RAM. And that's just a little bit high. If you look at the lines, that they were slightly bigger than the actual region itself, but pretty darn close to the actual value. So I want you to get in the trapezoid rule. Let's get down how they express these two methods in your calculus textbook. So for the TRAP rule, if we think about all those trapezoids stacked up next to each other, we have an h over 2. That's your 1/2 your height. And then the y at 0 and the one of these y at 1s, those two would be the first trapezoid, and then the other y1 and one of these y2s would be the next trapezoid, and so on and so forth. So the last trapezoid has the interior side and the exterior side used only once. And then, of course, if you want to just do an LRAM and RRAM approach, then you can just find those. So in our example, we had an LRAM 4 and an RRAM 4. That's what the ends were. And then we just took those two values, added them together, and divided by 2 to find their average. So either one of these methods would find your trapezoidal approximation. And so that trapezoidal approximation, that gives us a better approximation than what we've been using right now. This is at the bottom of that first page, and I just want to just practice drawing the trapezoidal approximation and connecting it to concavity. So let's just say here that we're going to do 3 subintervals, okay, from 0 to 6. So if we're going to do 3 subintervals, which means 3 trapezoids, then each trapezoid is going to have a width of 2. So for the first parabola here, we have this concave down shape. It looks kind of like a frown. So we're going every 2 boxes on for the width of that interval. And so when we connect those dots, we can see the trapezoids there. And we can see that when we do a straight line connection from dot to dot on a concave down function, we create some gaps in here. And so when we have that concavity to be concave down, we get an underestimate. Okay, so that's got a concave down shape, but that concave down means the second derivative is less than 0. So that's our underestimate. Our trapezoids are going to be underneath the function. And so let's try a smile now. This is concave up. And so if we again have a width of 2, and then we start to connect dot to dot, we can see that as we draw that straight line from dot to dot, it extends above the function. So this would be an overestimate. So when we have a concave up, which we identify by a smiley face, or our second derivative of greater than 0, then we have an overestimate for our approximation. And if we have a linear function, then if we're starting to connect the dots, we travel right along that function. And we really don't even need to subdivide in this case. We could just do one big trapezoid. But we could do separate trapezoids as well. So this would give us an exact value because the region underneath the function is geometric in the first place. And so this is no concavity. It's not a smile. It's not a frown. It's just no concavity at all, no bending at all. And so that's our second derivative equal to 0. So just to kind of connect the approximation method with the concavity here in terms of being over or under the actual value. Okay, so now we're going to try 2 problems. The first problem is applying the trapezoidal rule with equal subintervals. And we have a tabular method here. So we have this bobsled. It starts out at rest, and then it starts to slide down the hill, and it picks up speed as it's sliding down the hill. and so it picks up speed in this fashion. It's not exactly pretty. Doesn't look like it fits a function exactly. These couple points look like they're a little out of whack, but that's okay. So I'm just going to connect those points, and so we want to approximate the region underneath that graph. And so if we draw trapezoids underneath each one, you can see that those straight dot-to-dot segments really match this closely. So we're going to get a really accurate estimate here. So let's go ahead and set up our LRAMs and our RRAMs. So our LRAMs are going to look like this, and there are 8 subintervals there, and our RRAMs are going to look like this. So go ahead, if you need to stop the video to draw those out, go ahead and draw those out. So we gotta ask yourself, where do the rectangle heights come from? You know, how do we know how tall this is, and how tall this is, and how tall this is? And the answer is that we look up here in the table. And so for the LRAM, for this one, what table values will you use? Well, this first table value is 0, and then the next one is 4, and the next one is 10, and the next one is 18, then 25, and 37, and 48, and 60. So we're using all of the table values from the first to the 7th value. So we're not using the last one, basically. And for the RRAM, starts out with a height of 4 and goes all the way to a height of 70. So for the RRAM, we're using table values from 1 to 8. So now we can go ahead with our width of 1. We can go ahead and calculate our LRAM values and our RRAM values, and divide them by 2. Or you could use the trapezoid formula. And so I'll go ahead and stop the video and do the calculations. So you're either going to calculate LRAM and RRAM, add them together and divide by 2, or you're going to use the trapezoid formulas. And then when you come back, you'll see the answer. When you start the video, you'll see the answer for the TrapRAM. The final answer should be that the bobsled distance traveled is 237 feet. This next one is an AP calculus question from 2011, and they like to do questions like this. They have unequal subintervals. So now what happens is using the trapezoid equation becomes really difficult, because that trapezoid equation is set up for equal widths. So we have this data here. It's another tabular method. And so when we graph this data and draw a smooth curve across those points, it looks like that. And we're going to go ahead then, that's our TrapRAM right there, connecting the dots. And you know, I would estimate that this is actually an overestimate, because we have just a tiny gap here, and then we've got some pretty significant flaps. So we can go ahead and set up an LRAM and an RRAM. So for the LRAM, we're going to use the left hands to create rectangles, and for an RRAM, we're going to use the right ones to create the rectangles. And so go ahead and stop the video and draw those in. When you come back, we'll talk about the approach for finding the areas. So after you've got those rectangles drawn, we got to talk about where the heights come from. So this first rectangle here, this height is 2. So that's going to come from the table here. And so the LRAM heights are going to be 2, and this is 2.5, and this is 3. So it's going to be this and this and this, these values. So an LRAM uses what I would call the left values on the table. In other words, it's not using this last value. Okay, it's using the first 3 values. And then the RRAM, we're going to use 2.3, 2.5, and 4.6. So for the RRAM, we're using 2.3, 2.5, 4.6. We're not using the first term, so we're using these right values, not using that first value. So we're going to use, for the RRAM, we're going to use the last 3. And then let's talk about the rectangle widths here. This width is a width of 10, and I got that by taking 10 minus 0. This rectangle width is a width of 30. So And I got that because it goes from 10 to 40. And so I got that from subtracting 40 and 10. And then this last rectangle width is a width of 20. So I got that by subtracting 60 from 40, or 40 and 60. So go ahead and pause the video and you're going to have to use your LRAM and RRAM approach here. You can't use the geometric formula because of the different widths. Go ahead and calculate your LRAM, your RRAM, and average them to get your trap RAM. So after you've done the calculations, you should get a distance of 164.5 feet. So just to summarize approximations, they're called rectangular approximations. They're also called Riemann sums, and we'll talk a little bit about that in section 5.2. Our strategies is we need to identify the region. We need to, there it is, so identified it and shaded it in. We need to mark the intervals along the x-axis and sketch the rectangles. And depending upon, like for instance, this is just one example. This is an LRAM. This is one of 4 examples that you could possibly ask to be sketched. Then we could calculate the areas of all the rectangles, and then we add all the areas to get the final answer. So at this point, you'd be ready for the 5-5 trapezoidal rule homework. It's just a day 1. That's the only day. We're going to move on to section 5.2 tomorrow.